Okay, welcome back, Physical Science 20. This is the last part. So we looked at determining latent heat and combining it with all of the thermal energy involved with phase changes or just heating or cooling in a particular change, and identifying the the key thing there is the heating curve or the cooling curve, figuring out what areas you're in. The last part here just talks about water. Most solids sink in their respective liquids, and that makes sense because if we remember back to one of the pictures that we had, solid, liquid, gas. So usually in a solid, all the particles are close together. In a liquid, further apart. Gas, really far apart. So this would be more dense than this, and this would be more dense than this. So most of the time when I put a solid into a liquid, the solid should sink to the bottom. And if I put a liquid in the gas area, of course the liquid would sink to the bottom too. So most solids sink in their particular liquids. For example, a solid iron sinks in liquid iron. This occurs because the particles of the solid are more closely packed than particles of a liquid, therefore making them denser. However, water is different. Ice actually floats, and we know that. And we know that during wintertime, of course, the top layer of a lake freezes and not the bottom part, so that fish can survive underneath. Water is one of the few substances whose solid is actually less dense than the liquid. This is based on the water molecules' chemical structure. Water molecules are kind of V-shaped and have two hydrogens attached to one oxygen. So it looks something like this. What happens here is that the positive side is slightly positive and the oxygen side is slightly negative. The hydrogen atoms in a water molecule have a small positive charge, as I said, while the oxygen has a small negative. This little symbol that you see here is the Greek symbol delta, and it's often used to demonstrate partially charged. You'll find out more about that in Chem 30. This occurs because the hydrogen atoms of one molecule are attracted to the oxygen of another molecule because, as you learned in grade 9, with static charges, opposites attract each other. However, at temperatures above 4 degrees C, water molecules tend to move too fast for these force of attractions to pull molecules together. At these temperatures, water molecules are relatively disorganized, as you see on the next page. So if we take a look, water molecules are kind of all over the place like this. So this would be liquid. So you imagine these particles constantly moving around, not really attracting each other a little bit, but being pretty disorganized like you see here. As the temperature decreases though, what happens is the molecules move slow enough for the forces of attraction to occur to a great extent. So again, so if I just redraw that, so here's your water molecule, right? Looks like a Mickey Mouse head almost. So positive, and if I draw a neighboring water molecule, HO, negative, negative. So you can see here that negative and positive attract. So you can even look here. See this hydrogen attracted to the oxygen. This oxygen attracted to the hydrogen. Hydrogen attracted to the oxygen. So what happens is that they slow down, and the forces of attraction therefore can really act now because they're not moving very fast. And if I look at this area, the water molecules are fairly close together, whereas here they spread out because they make this crystalline structure. So we can write molecules further apart, making the hexagonal structure. Whereas over here, So here we have moving fast but still close together. Molecules further apart making hexagonal structure. Forces of attraction occur due to slow moving molecules. So we could write that as a little note there as to what's happening. So they slow down, and when they slow down, they get attracted to each other, and they make this structure, which makes it less dense than liquid. Okay, so that's what I say up over here. The more organized water molecules of water and ice take up more space than the more disorganized molecules of water. So water expands as it freezes because it's making this particular structure. And you know that if you put a drink in the freezer, you have to be sure to take it out or else it could possibly blow up, explode, etc. Pipes in homes or under the street can break under the pressure of the expanding during winter time. When the water thaws, it flows out of the broken pipes, causing flooding and damage. And that's, of course, due to water's special unique properties because its molecule is shaped like this and is charged. It attracts to other neighboring ones when it's moving slow enough, i.e. when it's a solid, and actually expands to make this weird-looking structure as opposed to just simply randomly moving around when it's a liquid. All right, you should be able to do the rest of the 1.4 assignment. With that, there's a couple of calculations on there. Looking at the heating and cooling graphs, trying to find the specific areas, and then going from there. We'll see you again.